Okay, John, we are ready, so go ahead.
Hi, good day. Sorry that I couldn't be there. I was looking forward to it, but it didn't work out, unfortunately. I'm here today to talk about machine health monitoring using acoustic sensing at the edge. I'm from sound sensing. I'm the head of data science and machine learning. We are a small company based in Oslo. We are early phase. We have running for 2 years now. We have backed by a strong team of engineers, and, sales developers, and of course, a large team of investors. So what we focus on is condition monitoring, which is making sure that machines, mechanical machines especially, operate correctly. And we focus on commercial buildings. This is technology that is often used in industry, everything from oil and gas to manufacturing, process industry, and so on. But we are targeting commercial buildings. You are in a building, a conference building right now. It has a lot of facilities that hopefully you as a tenant don't notice. Things work as they should, and you don't notice any problems. But this is actually a continuous job for the building manager and the janitors and the technical staff to make sure that it is the case. If you have a large building, things do go wrong all the time over the year and over the many years. So there's fresh air that needs to work. There's heating and cooling. There is lighting. There's drinking water, hot water, and many other things. And we focus on the equipment that's centered in what's called mechanical rooms. So in a modern building, a lot of the equipment that make these services work is placed in what's called a mechanical room, technical room, where you have the large parts of the ventilation system, of the pump system, cooling systems, and so on. So here in this image, we see actually on the left side this big box of many things that you can open. Is actually the air handling unit of the ventilation system, which is a core part. If that stops to work, you can have a severe reduction in energy efficiency. You will have poor air, either too cold, too warm, not enough oxygen, too much debris. And in the bit kind of middle to the right is actually part of the ventilation system, which is using pumps. So that also needs to work. And far in the back, there's pumps for other systems. So we place sensors into these rooms, and we use sound because it enables us to monitor an area of machines in combination with vibration sensors, which are point-based for each individual machine. So machines fail in many ways. You can have failures that are, at least with a given sensor modality, unobservable. So those are, of course, by nature, not something that you try to do some detection with. You can have, I'm going from the bottom, you can have failure events, which where you have there's a sound or there's a change in temperature and so on that only occurs at a specific moment, and then the problem is unobservable after that. This could be if there would be like a spark, for example, where the spark isn't normally a problem, but maybe it didn't cause the thing to fail immediately. You could only hear a little spark, and those are tricky to detect because they're rare, very rare. And you can have gradual shifts. You always have this in some way or another in mechanical system, where you have, for example, bearings that wear out over time. You have belts that wear out over time. The impellers in pumps, these have a tendency to gradually decrease. And the models that you use there are relatively simple. It's about getting the right quality of data, often over many years and for many equipment types. It's about trend fitting and predictive models. We focus mostly on the top here, which we call a state change, where you have a relatively abrupt failure. And this could actually happen at the end of a gradual shift. For example, if you have a bearing that's over many years has been operating okay, towards the end it might lubrication might have gone out, and at the end it starts to deteriorate faster, and at some point it will deteriorate quite quickly, and this is a threshold, a state change that we can detect. And then one can also detect that at some point it might actually break down, it might seize, like lock, and we have actually detected a few of these problems in production ventilation systems. And the techniques that are used there are what's called anomaly detection and change point detection. So this is what we will focus on today. So in order to understand anomaly detection, let's contrast it with classification. So with classification, you typically use supervised learning, where you have label data, you have examples in the binary classification, you have examples of, you could have normal data, or you could have abnormal or failure data. If you do this with classification, your classifier will create a decision boundary between these known classes and these known samples. So this is shown to the left here, where this example, the training is these blue dots in the center and the red dots on the left side. However, if we would get new sample points in this feature space, if we would get new sample points of failures on the right side of this normal cluster in the center, the classifier would classify this as normal because it falls on the normal side of this decision boundary. So, and this is a big problem when it comes to typical failures out in the wild, that binary classification will tend to fail on novel anomalies. So this approach is not suited for that reason. And the other problem with classification is that it requires a large amount of labeled training data. And these failures are, although they are a problem and for an operator happens all the time across their buildings, they are quite rare. Failure might happen in a given machine once per year. And each failure is typically different. So there's a large amount of variety. And to approach that with classification would take years and years and years of just data collection. And hopefully you then would represent all the possible types of failures. But in that time, the world has progressed and machines have become different, processes are now operated differently. And so it's a game that you cannot really win. So instead, what one does is, for the majority of cases, is to apply some sort of anomaly or outlier detection, where we model the normal data only. So this is sometimes called one-class classification, because we assume that the training data is predominantly normal, potentially with some contamination, that is called, if it's non-normal samples in the training set. And then we model only the normal class. So it will create it will only treat things that are close to the normal as normal, and everything else as abnormal, including things that have never been seen before. And this needs only normal data, at least in the training samples. Of course, for hyperparameter optimization and for validation and evaluation of performance, you do want to have some labeled samples, but you can get pretty far with maybe just 10 examples. And it will to just tell you the rough, the expected performance of this, because it's not needed for the optimization of the model itself, which is much more data hungry. And typically, in classification, requires 1,000 samples per class and hundreds of samples per each individual subtype inside the class. So this handles novel problems well, which is very important. So that's anomaly detection, and that what we will focus on. Try to introduce it because it's not as common as classification when it comes to edge processing or other processing. Now, another challenge, apart from the limited data that one has in these scenarios, is that the sensor modality which we use is often sound or sometimes vibration. That has a very high data rate, 48 kilohertz, for example, audio sample, or maybe even 96 kilohertz for some vibration measurements in ultrasound. But the parameter that we're interested in is, for example, the pump operating state. Like, is this pump in a good operating state, or is it not? Maybe it has there's air coming into the system. We would want to be able to detect that, and we don't care about it at the microsecond level, which is what audio sample rates are. Neither the millisecond or even the second. These scenarios that we are operating in, if we can alert people within 10 minutes or even 30 minutes after something is starting to happen or has happened, that is already great. So that's the output of our system is much lower. So that's a downsampling factor of 172 million times. So we need to do that in a smart way that provides the information and processes the data efficiently. And then there's even longer term. When we're talking about this gradual change, we even want more long-term time series. So, for example, bearing wear is often measured once per month. So, because it's something that happens over 5, 7, maybe 10 years, more data is not, more fine-grained resolution is not really needed to make those trends. So sensor data is very high frequency, and we are doing this with IoT systems. So basically our edge challenge is where is the boundary between our edge system and our cloud system, especially when it comes to the data rate. What is the data rate that we are transmitting between these? Because this influences the cost of transferring data. It influences what radio technologies are available, or transmission technology. And it influences the battery lifetime, because it tends to be that sending data is one of the most energy costly things that the sensor does. Also important to understand in this anomaly detection world is that the models are not static, because the world is not static. So your office over a day has different patterns, operating patterns. For example, ventilation systems are typically off during the night because it doesn't need to run. It might have what's called demand controlled ventilation. So it means that during the day, as people come and go and use the meeting room and so on, the ventilation system runs at different speeds in order to maintain quality, but at the lowest possible energy efficiency. So it means there's a dynamic system that's just during the day. And then during the week, often people work maybe Monday to Friday, or and Saturday and Sunday. There's not so many people, or you have alternate uses of the same building at that time. So in this case, it causes weekly variations. And of course, the weather and the seasons, summer versus winter, causes a big change in a building's operation. For example, in Norway, most of the time you need to heat your space because it's a relatively cold place. But in the summer months, there are some times where you mostly need to cool your space. And this is actually, the systems are often separate. So different systems are in use in the winter versus the summer. So that means that our models need to update continuously. And so this is illustrated here, where we have our data stream, distributed data, for example, per day in blocks. And we need to run training. We need to have some historical data to understand the normal, what is normal. And then we input this to the training process. And then when today's data, for example, comes in, we'll use the model for using the preceding week or month. And we'll use that to determine how, if things are going okay or not. But then tomorrow, we'll basically repeat the process. We'll look back the same amount of time, and we'll create a new model. The models are continuously shifting. Of course, they are, unless there have been abrupt changes in the pattern. They are not very different, the models, but they are different instances. They compensate them for the change, especially over the seasons. So there's a range of models, and each model is also device specific, because what is normal for one device, for example, mounted in one ventilation system, is not the same as the normal for another device mounted in another ventilation system, which is in a different building, different operating parameters, and so on. So there are many models. We're not talking about a single model. We're talking about one model per time period per device. So this is thousands, tens of thousands of individual models for a small fleet of So how does the edge fit into this? So I'll talk about three. Like edge AI is a big topic in many ways. Talk about three kind of aspects of it. Edge pre-processing, doing processing on the edge. Edge inference, where we run some trained model, typically trained in the cloud, and then running inference on the edge, and then edge learning. This is very different. It's important to be specific when we're talking about edge AI, like what pieces of AI do we use, which are on the edge and which are in the cloud, and how do they interact. So we have our own developed sound sensors. DB20 has a built-in 4G cellular modem. So it has internal battery for 1 week, and 12 or 24 weeks for long-term use. This is not a battery-powered device, at least in production setting. But it's typically then powered inside or by the same things that power the machines. And it supports edge pre-processing and edge inference. So when we do this acoustic anomaly detection, we have a basic flow of data. So you have the sensor installed in a location of interest. There's some ventilation shaft behind, and there's some valves here of a cooling system in the front. And we have some sound that comes in. This is a waveform. It can be converted to a spectrogram, which we see here. We can separate the processing of this as sort of feature extraction, where we're going from the quite complex data into smaller set of data that is, it might be human understandable, or it might not be, depends on strategy. This could be a learned step, or it could be a manual engineered step. And then we do some sort of anomaly score, which is basically how abnormal is that we're currently getting with respect to the typical pattern. And the typical pattern in this context is then for the preceding week or preceding month, something in that time period. And then we do some sort of thresholding in order to convert this to a discrete event, such that we can raise an alarm when something has happened. So here's illustrations. This is from the Open Case 21 dataset. Where in the top you have a pump running normally. Not sure how well you see this, but it's a relatively constant pattern. In the middle, or 2/3 up on the y-axis, there's a kind of straight band going along it. Also at the bottom is. In the malfunction case, this what was a straight band has kind of split. So something has shifted a little bit up in frequency, so on the y-axis. Some parts are now more energetic, a little bit lower frequency. And there's some sort of undulating pattern here. So going up and down, up and down, up and down frequency. These are different. This is something you would want to do. I'll show one example, another case. I hope sound works. Share sound. not that great. That's fantastic. I tried to preload it. I have no idea why there's ads. It's even on my own private YouTube channel. It is ridiculous. Okay, I am very sorry. I hope someone at Google is too.
Se for deg at det nye 5G-nettet fra
Ads.
Telenor vil ha så mye kraft og fart.
Yeah, I see. Hope you hear now the normal operation, the veering sound. Now we are introducing a fault. We can hear that the sound is relatively similar, but it drops in frequency. It has to work much harder to pump now because the inlet is blocked. And we can do the same with the outlet. And then this primarily this is, in this case, the anomaly is a shift in frequency, a little bit of a shift in the time patterns as well, but small. And then it's detected by the sensor and we flag anomaly. We use these test jigs as controlled tests so that because failures happen very rarely, it's very useful to be able to introduce them in a representative manner in the configuration. So we build these test jigs that represent typical systems, and we use them for data collection. And we also test. Okay. So how to realize such a system and how how does the edge in here? So we have the raw audio coming in the sensor, and it's a very large data rate. So if you stream this, it's around 240 gigabytes per month, which is 4G, very cost prohibitive, completely useless use of video costs. So what we do in the edge preprocessing case, we convert this down into a spectrogram, which is a time frequency representation, showed you before, of the sound. It becomes such an image. You can also interpret it as a human with some training. And if you use 150 millisecond resolution, some research has shown that it's not possible to recover speech anymore. So it's a privacy compatible representation. And if you have it uncompressed, it's 14 kilobytes per minute. And we use some compression on this, get down to 120 megabytes per month, which is a very manageable amount of data to send on 4G or Wi-Fi or wireless transport. And it's also most 2,000 times reduction in bandwidth. It serves the majority of the acoustic information needed to detect problems. This is already a win. How can we go further? And so you can use stolen autoencoder in order to actually do the anomaly detection. The principle is that you, in the training case, here there's given numbers in, to learn to compress that encoder and decoder pair and reconstruct it well. Give an input that was not training, it will reconstruct this very poorly. Use this error then. And there are many variations proposed on this topic. It's very widely researched, for example, in the case conference. And here's just a couple examples where instead of trying to reconstruct the entire spectrogram, as shown at the left side, the classic one, you can try to, for example, predict a future time frame, or you can try to predict the middle, trying to fill in a spectrogram. And this they tend to do So now what we can do is we can put this neural network onto the edge device using something like Edge Impulse or using Byte, many tools or Xcube AI from ST. And this means that the model is being trained in the cloud, as I mentioned, per device and per time. And then we deploy it to our device firmware over the air. And then we can output the anomaly score directly from the device. What this enables us is we don't need to send all the spectrograms anymore, but it's important to realize that we still want to send some spectrograms because we need the training data in the cloud. So what we might do is go down to, say, 10% of spectrograms, one per. Then that's around 2 megabytes. But you need to use updates here. That will estimate here to be. So it's not a, you never win 100%. What we could do instead is to use a neural network which is not specific to the particular device and time, shown here in the middle. We'll do what's called representation learning, where you might use data from all the devices in order to learn the compressed representation and outputs for example, a 16-dimensional vector that's compressing all the information down. And